What's going on, everybody? We're going to talk today about intermolecular forces and how to know what sort of forces exist. So intermolecular forces are forces that occur between two different molecules. We've also previously talked about intramolecular forces, and intramolecular forces are thinking about things that happen within the same molecule. So if you are an English major and you think about an introspective person, it's someone that has a lot of thoughts and feelings and emotions that they're thinking about themselves. If we talk about like a work situation, you have like interpersonal relationships, that's it's in between two different people. So there's four different basic intermolecular forces. The first one's ion dipole, and this is where you have a polar molecule in the presence of an ion, and usually it's a cation. So we'll have some sort of polar molecule, and that'll be this dipole, and we'll talk a bit more about what this dipole actually means. And we're going to have it in the presence of, usually it's a positive, but it can sometimes also be a negative ion, and I'll show you what one of those examples look like. A dipole, so dipole, all that means is that we have two poles, and in this case it means that the molecule is polar, and as a result there is a partially positive and partially negative end to the molecule. Hydrogen bonding, this is where hydrogen is attached to a very electronegative atom, and so hydrogens become partially positive and attract other molecules. Those super electronegative atoms usually are oxygen, nitrogen, chlorine, bromine, any of the halogens. If we look at the periodic table, it's basically anything kind of in this top quadrant here, not really carbon, but nitrogen, oxygen, fluorine, sometimes sulfur would be included, phosphorus might also be included. Carbon's sort of the one that's not, so it's basically everything kind of to the right of that. London forces. These are called London forces or dispersion forces. And the way that London forces work is if we have some sort of molecule, so let's say we have some sort of molecule, what'll happen is over at any random instant, all of the electrons will sort of pile over to one side of the molecule. And so we use that sigma symbol to indicate whether something's positive or negative, but basically one side of the molecule at any given point in time will become slightly negative, one side will become slightly positive. It's sort of a weird one, but these ones we can say that all molecules have these. That at any given point in time, if there's electrons in a molecule, which all molecules have, the electrons can pile over to one side. An ion dipole force, I'll draw some little pictures here. This would be like if we had like a sodium atom present, and then let's say that we had, let's say that we had like an HCl molecule sitting somewhere. If we have this HCl molecule, we know that the hydrogen will be partially positive, the chlorine partially negative. And so what'll happen is this sodium molecule will actually drift over closer to this chlorine. And if there's a bunch of sodiums in that solution, what we'll start to see is that those will start to sort of surround that chlorine like this and sort of create like a network of all the positive things surrounding that negatively charged thing. Dipole, the way those work, I'll draw just a water molecule. That's the most basic example that we use. This has a dipole because it's asymmetrical, and we also have lone pairs of electrons. So what'll end up happening is these hydrogens are partially positively charged, the oxygen's partially negatively charged. What'll end up happening is something like this, where we'll start to see water molecules actually start to stack on each other like this, where these positive hydrogens are coming closer to this negatively charged lone pair of electrons. Now, the other thing that we also start to see with water is we start to see, because we have hydrogen attached to a very electronegative atom in oxygen, we start to see this network starting to be formed of these hydrogen bonds, where these bonds will start to try to attach to this oxygen. And that'll create sort of a more stable molecule of water. And then London dispersion forces, we have them there. So one of the other key things that I want to highlight in this video here is that you can have multiple different intermolecular forces in one molecule. So if we look at, let's take a look at a couple of these different examples here. Let's throw these up at the top here, and let's get rid of that little dot, and let's talk about them. So let's say that we had H2O. I already drew that, so we'll draw that one again. And we'll talk about all four of these forces and whether they're present. So if the question just says that we have H2O, we do not have, let's write out all four of the forces here, just for ion dipole, dipole, H bond, and London forces. So those are kind of the shorthands of each of those phrases. So let's go down here, and let's go, let's go down here. So with this water, we don't have an ion anywhere present, so we don't have ion dipole. We do have a polar molecule, as we talked about, like this. And so what we do know is that, yes, we do in fact have dipole-dipole. Do we have hydrogen attached to a very electronegative atom? Yes, we do. So we have hydrogen bonds, and we have London forces, because those are present in every single molecule. Moving over to CS2, we know carbon has 1, 2, 3, 4. We know sulfur has 6 valence electrons. And so we can see that, well, those two are going to bond up. This is going to bond up with this. So we're going to clean this up a little bit more here. And we'll end up getting a molecule that looks like this. I'm going through these rather quickly because if you're watching this video, I hope you've watched the previous videos where I draw Lewis structures and take you through a really slow process of doing that. So ion dipole, do we have an ion present at all in this molecule? We don't, so we do not have ion dipole. Is this molecule polar? Do we have any asymmetry anywhere? If we cut it down the middle, nope. Cut it through the side, nope. We don't have any asymmetry at all. This is a perfectly symmetrical molecule. Yeah, we have lone pairs here, but those are not on the central atom. And because they're both the same on both sides, we know that the pole will be equal on both sides. So we don't have a dipole at all. We don't have any hydrogens present, so we know we have no H bonds. And then London forces, we always have them. So we know that we have London forces here. Let's do one last example here. We have CHBrCl. Carbon has 4. Hydrogen has, let's add this here. Let's add a 2. We have carbon, which has, let's add 2 hydrogens. Let's make my life easy. 2 hydrogens. Oops. And we'll go like this, boom. So hydrogen has 1 valence electron. Bromine has 7. Chlorine has 7. Carbon has 4. So I can start to predict that this is what the molecule will start to look like. H, Br like this. It doesn't matter what side you draw them on. You could draw the 2 hydrogens on one side. And actually, I'm going to flip that once I show you kind of the example here. What we're looking for here, do we have an ion? No, we do not. So we don't have ion dipole. Is this molecule polar? We can clearly see that it's asymmetrical because he's a bromine versus a chlorine. So what we need to know is which of those two is more electronegative. Otherwise, which one's higher or which one's further to the right. So you see the chlorine's a little bit higher. So we know that the chlorine will have a stronger pull on those electrons. Now, if I draw my arrow like this, it's correct, but not perfectly correct. We can make this look slightly better if we draw the hydrogen, which is the very least electronegative. We can make it slightly more accurate if we do it like this, and we draw our arrow sort of like that at an angle. As long as it's pointing towards the chlorine, that's the most important. So yes, we have a polar molecule, and that means we will have dipole-dipole interactions. Do we have a hydrogen attached to a super electronegative atom? No, they are attached to the carbon, and I said that carbon is not super electronegative, so we don't have hydrogen bonding. London forces, do we have those? Yes, we always have London forces. So there's 3 different examples, as well as talking about what each of those forces are and how they work, and then also listing how they look like in a couple different molecules. I hope this was helpful, and we'll talk to you in the next one.